Generative artificial intelligence, GenAI, has the potential to improve healthcare quality and safety through automation that enhances patient care. Powered by foundation models, GenAI represents a paradigm shift away from traditional task-specific classifiers. The imminent application of GenAI in healthcare will be through well-defined, low-risk, high-value, and narrow applications that automate healthcare workflows using smaller foundation models. These models will be fine-tuned for different capabilities and application-specific scenarios, providing medical explanations, referencing evidence within a retrieval augmented framework, and utilizing external tools. The authors contrast this with a general, all-purpose AI model for end-to-end clinical decision-making, which will require greater research prior to implementation. They consider areas where, human-in-the-loop, GenAI can improve healthcare quality and safety by automating mundane tasks. The principles of implementation science will be critical for integrating, end-to-end, GenAI systems that will be accepted by healthcare teams. Following the release of OpenAI's Chat Generative Pre-trained Transformer, ChatGPT, the adoption of GenAI and foundation models has witnessed a notable surge. Foundation models receive text queries and generate text output in return, and have been studied for use in various medical research tasks such as operative and progress note writing, answering patient questions, generating clinical summaries, creating differential diagnoses, and understanding personal health data. However, these models have also demonstrated limitations, including producing medically inaccurate or nonsensical outputs, hallucinating facts, and propagating existing biases. Despite these limitations, GenAI is already being integrated into health systems. The authors argue that GenAI holds the potential to transform clinical medicine over the long term, but health systems are more likely to realize its immediate benefits by applying this technology towards improvements in quality, safety, and efficiency through well-defined, low-risk, high-value, and low-variation use cases. A frequent approach in AI development for clinical applications is the pursuit of use cases that require near-perfect AI performance. But the authors suggest that a more feasible approach is to focus on automating healthcare workflows using smaller foundation models. Harden, less than, Otropic greater than Frid 835 KY Garn type Zwotropic CDC deceased 1/4 Oloma Kyoto Acom slightly smiling face Otropis steam driver key deceased Caldwell Lakes 1/4 Otropic 1/4 type ID _off ZW men _OFFCKE 1/4 Zwamba. Opened _CTXT Kiamoino key 1/4 Acom slick close angle bracket K. Improving quality and safety at the point of care is a crucial application of generative AI in healthcare. By automating labor-intensive, non-diagnostic clinical and administrative tasks, generative AI can support healthcare workers and administrators in performing their duties more effectively. One approach is to create dynamic user interfaces that facilitate healthcare workers' interaction with complex medical data, including patient data, compliance manuals, and evidence-based guidelines. These interfaces can streamline interactions with multiple digital tools and sources of information, efficiently extracting and analyzing crucial information from vast amounts of patient data. This approach differs from training medicine-specific foundation models or using models for prediction, as it focuses on presenting an intuitive interface that augments clinicians' capabilities. The potential benefits of such GenAI-supported dynamic interfaces include improving adherence to evidence-based guidelines, reducing inter-provider variation, and provisioning the basic standard of care. Additionally, generative AI can help clinical engineering teams with healthcare equipment maintenance by transforming lengthy equipment manuals into interactive question and answer systems, enhancing engineer productivity and indirectly contributing to the equipment's working quality. Another key application of generative AI is in improving clinical documentation for clinicians and administrators. Generative AI's assistive writing abilities can reduce documentation burden by documenting specific medical terminology and increasing record accuracy. This can provide higher quality documentation and training data for future iterations of EHR foundation models. Examples of assistive writing applications include writing referral notes and prescriptions, generating concise summaries, and parsing medical records to synthesize clear, concise summaries of active and historical conditions. Recent work has demonstrated the ability of foundation models to extract key data elements from patient notes and reformat this information into a structured layout, aiding in filtering clinical trials. A prompt engineering framework has also enabled batch queries to process large volumes of pathology reports for structured information extraction and estimation without requiring extensive task-specific human annotation and model training. The application of generative AI in healthcare has shown significant potential in enhancing quality and reducing errors. Dynamic checklists, supported by AI, improve compliance with best practices during ward rounds in ICUs, reducing length of stay. For instance, AI-enhanced checklists for lung protective ventilation, LPV, can assess ideal body weight, tidal volumes, and adherence to LPV protocols, standardizing operative and ICU ventilator management. Additionally, foundation models can be used for data discovery, exploration, and extraction, reducing data siloing by translating different medical terminologies and data structures into a unified format. This integration can increase the utility of health system data, enabling predictive analytics and basic auditing. Implementing such systems requires a multidisciplinary approach, considering design, user experience, workflow integration, and performance monitoring within clinical workflows. The integration of generative AI, GenAI, in healthcare is a promising yet complex endeavor. It requires a thorough understanding of the potential benefits and risks associated with its implementation. GenAI systems can enhance workflow efficiency and user experience, but their impact on productivity, workload, and user experience needs to be quantitatively assessed in real-world clinical settings. The total cost of implementation, including monitoring, maintenance, and infrastructure adjustments, is also crucial to consider. Risks include hallucinations, omission, and bias, particularly algorithmic bias towards underrepresented minorities, which could perpetuate healthcare disparities. Techniques to mitigate these biases and ensure health equity are essential. Automation complacency is another area of concern. To address these challenges, a coordinated approach involving principles of implementation science and ongoing impact studies is necessary. While significant work remains, the potential for GenAI to accelerate quality, safety, and efficiency in healthcare delivery is substantial. The combined summary starts directly with the content, focusing on the key points from both pages. It begins by highlighting the various research papers cited, including their titles, authors, and publication details. The summary then delves into the methodologies and findings presented in these papers, explaining complex terms and concepts with precision. It highlights novel ideas, significant findings, and important arguments from the cited works. The summary also details equations, algorithms, and mathematical concepts, explaining their purpose and significance. It efficiently summarizes information from figures, tables, and graphs, connecting the content of these 2 pages to show the flow of ideas. The summary identifies limitations, assumptions, and future work discussed in the papers. It maintains a highly technical and professional tone, using precise language and domain-specific terminology appropriate for the field. The summary follows a logical flow mirroring the structure of the original pages, avoiding any introductory or concluding remarks. The combined summary starts directly with the content, without any introductory phrases, and ends without any concluding remarks. It maintains one-to-one correspondence with the research paper, adding no extraneous information and omitting no significant details. The summary flows smoothly and logically between the 2 pages, using precise language and domain-specific terminology appropriate for the field. It highlights novel ideas, significant findings, and important arguments presented in both pages, detailing equations, algorithms, and mathematical concepts, explaining their purpose and significance. The summary efficiently summarizes information from figures, tables, and graphs and identifies limitations, assumptions, and future work discussed. The foundation model capabilities encompass a wide range of functionalities, including data management, potential applications, associated risks, and mitigation strategies. Key aspects include high-throughput extraction of clinically relevant data variables from unstructured text, social determinants of health extraction, and the propagation of existing biases. User interface capabilities focus on decision support at the point of care, with concerns about inaccurate responses from pre-trained data models. To address this, RAG-based support is integrated to adhere to institutionally approved guidelines. The model's responses enable human-in-the-loop verification of model output, highlighting the need for domain-specific language models and their integration into electronic health records, EHR. Dynamic checklists promote adherence to evidence-based practice, and stakeholder engagement is crucial for user-centered design. The summary also touches on text summarization, sentence completion, and note writing assistance, emphasizing the importance of educating users about technology limitations and the need for a human in the loop to avoid biases and privacy issues.